Swayam Prabha. Digital India. Educated India.
Welcome. In the last lecture, we have started discussing the derivation of solution of the Rouse model, and we have been like halfway through. So, we will complete the derivation in this lecture. So, just to briefly recap, we are talking about the discrete to continuous transformation of the bead spring model. So, where we have a contour variable n equal to 0 to n, and we talk about the position of a segment r and t and the random force acting on the segment like this, and then the original equation is a partial differential equation with boundary conditions dou r by dou n is equal to 0 at n equal to n. So, I have already written this equation in a form of a linear ODE, actually a series of ODE, by doing a linear transformation where I define a function xp like this, such that it satisfies linear ODEs like this, and essentially we have derived phi p n to be 1 by n cos p pi n by n. So, this ODE is for p equal to 0, 1, 2 and so on, and we have written f p as zeta p by zeta 0 to n dn phi p n f r of n t. Okay. So, that is where we are so far. So, now take it further. So, now we have also obtained a value that we had earlier as p pi by n, where a was defined as a square as k p by k divided by zeta p by zeta, which is now equal to p pi by n squared, which means k p is equal to k zeta p by zeta p pi by n squared. Okay. So, we have found the k p. The only thing is that the zeta p is still to be found arbitrarily. So, if the whole procedure seems to be somewhat confusing to you, keep in mind that we are only trying to write the PDE into a set of ODEs. We do not really care about getting a unique value of the XP, and therefore, we do not really care about a unique value of the constants we have like Kp and zeta p. So, they are arbitrary as long as they satisfy the ordinary differential equation. Okay. So, even though we have established this equation, the zeta p can also be chosen arbitrarily. Okay. So, how do we get zeta p is the following. So, we choose zeta p such that we have f p x t f p x 0 follows a relation similar to what we had for the random functions f r to zeta p k b t delta t. And now, since we have defined f p as zeta p by zeta and we know what phi p n is. So, it is zeta p by zeta like that. And therefore, if we are interested in something like f p alpha t f q beta 0, I am doing in somewhat general terms. Ultimately, we want f p x t f p x 0 autocorrelation, but we are doing in general terms. Alpha and beta represent the coordinate directions and p and q represents the indices of the solutions that I am looking at, different values of p essentially. So, this would then be equal to zeta p zeta q by n square zeta square. So, we have n zeta coming out here. So, we have n square zeta square and we have 2 integration again to retain the cross terms. I define the contour variables as n and m again to retain the cross terms, and then we have in the middle cos p pi n by n cos q pi m by n, and then we have f r and t, and we are looking at not really the whole vector, but the alpha and beta components of these vectors. So, we can write this as f r alpha and t, f r beta m 0, and this quantity should be equal to 2 zeta k b t del t, and then we should have a delta of alpha beta, the Kronecker delta, because if it is a different direction, then the forces, random forces are uncorrelated. Only when they are in the same direction the forces are correlated. And then we also have a delta of n minus m, because at different points along the contours, as long as the distance is not 0, the FR values are uncorrelated. And then this term I can write using the formula for cos A plus B and cos A minus B as half of cos that is plus cos that is minus. Okay. So, now this looks somewhat complicated, but we wrote it just because we wanted in a general form. But now you can see that we are integrating over delta of n minus m. So, if I integrate over m, I can replace n by m inside the integral and I can remove the integral over m. So, I will essentially take this away and I will replace m by n there, and essentially then what we have is f p alpha t f q beta 0, that is what we started with, is equal to zeta p zeta q by n square zeta square, and then we also had a 2 there from the cosine terms, and then we have integral over 0 to n over dn, and then we have two terms here. The first term is cos of p plus q n pi by n, and the second term is cos of p minus q n pi by n, and then we have 2 zeta kbt delta t, delta n minus m is taken away, but we have delta alpha beta is still remaining there. So, now we can go on and look at the integration we have right here, but we have now integration over cosine functions. So, if I look at the integration over the cosine functions, this would give me on integration, other things are anyway constant, this will give me on integration from 0 to n. Now, if you notice here, the second term will always be 0 as long as p is not equal to q, because we will have something that is a multiple of n pi or pi. So, this will be not equal to 0 only when p is equal to q, and in that case too we have to take a limit using the L'Hopital's rule. And if I look at that, then I can write this as something like, if I let p minus q is equal to some r, then we have the limit r going to 0 sine of r pi n by capital N divided by r pi by n. So, it is 0 by 0 form. So, we need the L'Hopital's rule. So, this is equal to divided by pi by n. This will be equal to n because cos will become 1 and we have cancellations here. So, between the limits 0 to n, this becomes equal to capital N when p is equal to q. Now, if I look at the first term, now it is always 0 except when p plus q is equal to 0. Now, since p and q are both positive integers, this means this is not equal to 0 when p is equal to q is equal to 0, and in that case this is equal to n when p is equal to q is equal to 0. So, as a shortcut I can look at this entire term and I can write as the first term as something like n multiplied by delta p0 delta pq. Delta pq means it is only non-zero when p is equal to q, and delta p0 means it is only non-zero when p equal to 0. So, if I multiply both, it means the condition p is equal to q equal to 0, and the second term is n multiplied by delta pq. So, we have n multiplied by 1 plus delta p0 delta pq. Okay. So, now I will plug that back in this equation and I will have a simplified relation which would be f p alpha t f q beta 0 is equal to zeta p square by n square zeta square plus multiplied by 1 plus delta p 0 multiplied by n multiplied by delta p q multiplied by zeta multiplied by kbt multiplied by delta alpha beta multiplied by delta t. Okay. So, this is what this thing becomes. You can see that 2 has cancelled here, that is why we do not have a prefactor in this equation, and now you also have a cancellation of n zeta and we get something like zeta p square by n zeta in there. So, now since I am interested in f p x t f p x 0 delta p q is equal to 1 because I have set p is equal to q, and delta alpha beta is also equal to 1 because we only are looking at x coordinates. So, we have zeta p square by n zeta multiplied by 1 plus delta p 0 kbt delta t. Okay. So, now we have demanded that f p x t f p x 0 is equal to 2 zeta p kbt delta t. Therefore, if I compare this now, what I would get so, when we have to look at two different cases, when p is equal to 0, then we have this becomes 2. So, it is 2 zeta p square by n zeta. To make it equal to 2 zeta p, we have to take zeta p is equal to, for p is equal to 0. You can plug it here. You can see in this case zeta p square by n zeta 1 plus delta p 0, this becomes equal to n zeta square by n zeta multiplied by 2, that is equal to 2 n zeta, which is 2 zeta p. So, it works well, and zeta p is equal to 2 n zeta for p not equal to 0, because in this case we have zeta p square by n zeta multiplied by 1 plus delta p 0. So, 1 plus delta p 0 is 1 in this case, because p is not equal to 0. So, this is 2 n zeta square by n zeta, which is equal to 4 n zeta, which is equal to 2 times zeta p. Okay. So, if I have taken zeta p is equal to this, we get the relation that we wanted to get, and therefore, we have one way to identify the zeta p as well. I have already identified the relation for k p, and now we have the relation for zeta p. So, with that I now have the complete representation of the Rouse model into a series of ordinary differential equations, where we know how to get the constants k p and zeta p. Okay. So, we will start from this point in the next lecture, and then try to illustrate that how this kind of math become useful to us, because of course, it is complicated. We are trying to write a partial differential equation into a series of ordinary differential equation. Of course, we said that PDEs are difficult to solve than compared to ODEs, but of course, we could have done a numerical solution. So, there must be some other advantage of going in this particular means, and that is what we will demonstrate in the next lecture. Thank you.